Hi there! In this video we're going to talk about the Poincare disk model. We'll introduce the notion of inversion in a circle, discuss the fifth postulate and the hyperbolic plane, and talk about the sum of angles in a hyperbolic triangle. Let's get started. Inversion in a circle is an operation that was invented by Jakob Steiner in the late 1880s. It's a very beautiful map that has a lot of the properties of a reflection, just like we've studied in the rest of the course. Let's have a look at what it is. So, the inverse of a point A in a circle C with center O of radius r bigger than 0 is the following. It's a point I on the ray OA such that OA times OI is r squared. Additionally, we're going to map the origin O to the points at infinity. So infinity and the origin will kind of switch places. How do we go about constructing such a point? So, given a circle O with a point A, we proceed as follows. So we take this point A, we take the ray OA. Now at A we construct a perpendicular out to a point T, and from that point T we construct a tangent. So that tangent is going to intersect the ray OA at the point that we're looking for. So what do we have? We have that these two triangles are similar. So OAT is going to be similar to the triangle OTI. And if we look at what that does, we have that the ratio of OA to the radius OT is the same as the radius OT to OI. So if we multiply across, we wind up with OA times OI is OT squared. Now we know that OT is a radius, so this winds up being r squared. Okay, and notice that this property is symmetric in A and I, right? We get that A maps to I, but also going the other way, I has to map to A. So these two switch, and that property is a lot like a reflection. Okay, let's see what else inversion can do. Inversion has a lot of beautiful properties. Here's a picture from our textbook. So our circle here is this dotted circle C. Our origin is here at O. And this figure is trying to illustrate many of the beautiful properties that inversion has. So for example, circles inside of C invert to circles outside of C. If we have a circle passing through the point O, then it's going to invert to a straight line passing through the circle of inversion. Okay? Lines passing through the center of the circle will invert to themselves, and circles orthogonal to the boundary will also invert to themselves. Okay, so there's lots of beautiful properties that inversion has, and we're going to get into the proofs of these in class. Okay, now let's introduce the star of the show. We're going to introduce the Poincare disk. So in the Poincare disk, the lines of the hyperbolic plane are diameters of the disk or circles orthogonal to A. But what is this h squared and A business? So the hyperbolic disk model is the geometry whose points are points inside the unit disk, so x squared plus y squared is strictly less than 1. The boundary circle A is when it is equal to 1, and we call this the absolute. The transformation group of the geometry is defined to be inversions in circles orthogonal to A. Okay, so we have a circle here that we're calling the absolute. And if we have a circle perpendicular to it, so making a 90-degree angle, then a transformation of the hyperbolic disk model is going to be inverting with respect to that circle. That will wind up taking the inside of this region onto its complement, onto the stuff over here. Okay, so when we invert in that green circle, we switch the two halves of the hyperbolic disk. Okay. So, now that we've got this notion of lines and transformations, what does this say about the theory of parallels in the fifth postulate? So given a pair of points A and B, in the hyperbolic disk model, we have a line passing through A and B, and if we take the tangents to A and B, we get that they intersect at a point P. Now, here's the interesting thing. Any line through P is going to live in between those tangents. Right, so there's a line through P. There's another line through P. There's another line through P. So what we have is that any line through P actually is going to avoid A and B. It's going to avoid this geodesic. So given a line AB, there's going to be infinitely many lines that pass through the points P but do not intersect AB. So Euclid's fifth postulate does not hold in the hyperbolic plane. Given a line AB and a point P, there are infinitely many lines through P not intersecting AB. This is very different than what happens in the plane. In the plane, in the standard Euclidean plane, given a line AB and a point not on it, there is a unique line, the parallel through P. But here in the hyperbolic plane, there's infinitely many. So it's very remarkable. I want to show off one last property of the hyperbolic plane, which is that sums of angles behave differently than we'd expect from the Euclidean case. So here we've created a hyperbolic triangle. We've got A, B, and C. And I want to point out that if we were to join this up to make a Euclidean triangle, right, we'd have three straight lines, AC, CB, BA. And notice that the curved arc here, this hyperbolic line, is on the inside of that Euclidean straight line. So what we obtain is that these angles, the angles at C and B, are slightly smaller than their Euclidean counterparts. Okay, so in a hyperbolic triangle, the sum of the three angles adds up to less than pi, which is quite different than what we'd expect in the Euclidean case. So we're going to spend a lot of time exploring hyperbolic geometry. This is just an introduction to the properties of the Poincare disk. Thank you for watching.